Okay, good morning, everybody. I'm glad to see you here once again. Today we are going to have two sessions regarding our research work in this center. And during the first part of these sessions, we are going to hear 6 speakers. And before we start, I just would like to remind all the speakers that the time that is meant to be used is around 20 minutes. It means 50 minutes for the talk and 5 minutes for the questions and answers. So let's start with the first talk. The first talk will be given by Diana Čučak. Diana is a PhD student in our research center, and her main research topic, wide bandgap devices like gallium nitride and silicon carbide. So Diana, please.
Well, thank you, Mr. Chairman. Good morning, ladies and gentlemen. Today's presentation will be about physical modeling and optimization of gallium nitride high electron mobility transistors for high-frequency application. So, first of all, I will address why gallium nitride HEMTs are so suitable for high-frequency applications such as envelope tracking and envelope elimination and restoration techniques. And afterwards, the objective of this physical modeling will be presented and explained. Further, we go to the main part of the presentation, which is the obtained model for gallium nitride HEMT with a field plate, so-called field plate structure, that was designed and manufactured in Fraunhofer Institute in Germany. So in this part, we have, let's say, 3 key points. The first point is related to determination of the 2D gas dependence on the gate voltage, or how do we control this 2D gas by the gate voltage. The second key point is the model for the drain current dependence on the applied drain source and gate source voltages. And the third one is related to parasitic input, output, and reverse capacitance in a device. Finally, we will summarize all the obtained results and present some future work steps. So let's start. Why gallium nitride device in envelope tracking and envelope elimination and restoration? Well, as you probably already know, envelope tracking and envelope elimination and restoration techniques employ this dynamic power supply for radio frequency power amplifier called envelope amplifier. And this envelope amplifier needs to have, on one hand, fast dynamic response in order to track very fast signals, and on the other hand, high efficiency. So we propose synchronous buck topology with gallium nitride high electron mobility transistors as switching devices. So, what is the objective of physical modeling in this story? Well, the objective is, okay, as we know, here on the right-hand side you can see the cross-section of one gallium nitride device with this so-called field plate structure, which is actually this extension of the gate electrode with a material like silicon oxide or silicon nitride in our case below. Every switching device is actually described by its electrical characteristics, such as drain current, input, output, and reverse capacitance, and their dependencies on the applied voltages. So if we could, we know that our power losses are determined by on resistance and these capacitances. So if we are able to provide the connection between these capacitances and on resistance on one hand, and on the other hand, design parameters of the device itself, then we could obtain the connection between the losses and the design, which means that we could directly optimize the design of a HEMT for this particular application. So that's the goal. So now we have to go to the model. And in order to present the model, it is necessary to start with the basic physics of semiconductors. First, I would like to point out some really unique features of gallium nitride devices. And this is just on the left-hand side, you can see isolated aluminum gallium nitride heterojunction, which means that it doesn't even have applied a gate contact. So it's just a heterojunction with aluminum gallium nitride undoped and significantly thinner than gallium nitride layer. So what happens is actually that when we make this structure, already high polarization field, electric field exists, which is built inside the material. So this electric field actually pulls the electrons from these donors, like surface states, and forms so-called 2D gas, which is also called the heart of the HEMT. What does this mean if we analyze the energy band diagram? Well, this means that in this equilibrium state, we already have in the quantum well 2D gas, and we have electrons that occupy the first energy subband, which is below the Fermi level, and this means that the channel is already opened. So this is why these devices are known as normally on devices with negative threshold voltage. So now we can say, okay, how does the band diagram look like if we put a gate metal and if we apply some gate voltage? How do we turn off the device? Well, we turn off the device by applying negative gate voltage, pushing this energy band diagram above the Fermi level, and placing both of these possible energy subbands for the electrons above the Fermi level. If we want to turn on the device, what happens is that we increase the gate voltage, we actually shift the band diagram below, and we have electrons that contribute to the current of the 2D gas, which occupy this state here. So now, as I said, it is our goal is to determine, okay, how can we control this 2D gas by the applied gate voltage? Well, in order to do that, we actually apply basic laws of physics. We apply Poisson's equation for Algan layer, we apply Poisson's equation for GAN layer, we apply Gauss law charge for charge conservation here at the heterojunction, and this is what we obtain. Here you can see the 2D gas dependence on the gate voltage for 3 different aluminum mole fractions in an Algan layer. You can see that this is a threshold around -2, and you can also see that there is a point where this 2D gas saturates. Why does that happen? Well, our Fermi level, when we apply the gate voltage, actually this is its dependence on it. So at one point, what will happen for gate voltage around 0.7 is that our Fermi level is going to become equal to the height of the quantum well. And this means that if this happens, not only these electrons here will saturate, and electrons in the aluminum gallium nitride will be actually capable of contributing to the conduction. So this means that we have a parasitic mass with conduction through the Algan layer and saturation of the 2D gas. So this is the story about the 2D gas model, which is necessary to move on. Let's see now what happens, how do we model the current? Well, first of all, before we present the model for the drain current, it is necessary to point out that this is extrinsic model, which means that these contact resistances need to be taken into account, and also so-called drift resistances, which exist between source and gate and drain area. How did we manage to model this, and how did we even discover this? Well, thanks to our colleague Ashu Wang from ISOM Institute, who actually simulated this electric potential distribution along the channel, where we clearly saw, for different drain voltages, where we clearly saw this constant voltage drop and model this drift resistance. In the model for drift resistance, this 2D gas value that was used, that occurs here in the drift areas, is actually the value for the 2D gas when the gate voltage is 0. So let's move to the drain current, which is one of the key points in the model. The drain current is modeled in this way for the linear part, which is the area of interest, where you can see that Vd is the drift velocity of electrons in the channel. This is the applied model for the mobility. And this is the 2D gas dependence that was already derived, but now we need to take into consideration this voltage drop in the channel since we are applying drain to source voltage. If we do the integration, perform the integration, we obtain the full model. On the other hand, in the saturation region, since it's not the area of interest for us, a really basic model was used, where only this drift velocity was replaced by the saturation velocity of electrons for electric field in the channel higher than the critical one. And this is what we obtained. We are comparing model with the measurements for two Fraunhofer transistors that had the same design. And as you can see, we have obtained the highest error here in the saturation part, which is not the area of interest for us. And we have obtained really good agreement in the linear part between the measurements and the model. So let's move to the capacitances now. Capacitances were actually quite challenging since we didn't know where to look for their origin. And here, first of all, we started to analyze the measurements that were performed in University of Valencia. And we analyzed first this gate-to-drain capacitance, or known as Miller's capacitance. And again, ASHO simulations helped us because in this case, you can see when he simulated the electron density dependence on the position in the channel when the transistor is off for gate voltage equal to -3 volts, we were able to finally clearly distinguish two regions of the capacitance. The first one is the region up to VDS approximately 16 volts, where we are actually depleting the 2D gas under the field plate structure. And the second one is this fringing area where we're just slightly fringing or extending the depletion area towards the drain. How did we model this? Well, we actually applied the same methodology as we applied to determine the 2D gas when we are changing the gate voltage. We just applied it for the mishamped structure here. Since we are changing drain to source voltage and gate to source is being constant, basically we have obtained the 2D gas depletion model dependence on the applied voltage. And this is what we have obtained. And this has a really good correspondence regarding the voltage VDS when this 2D gas fully depletes. It is around 16 volts. So now fringing. Fringing is necessary in order to complete the model for the Miller's capacitance. And it was really difficult because we needed to find the relationship, analytical expression that connects this extension in the depletion area with the applied drain to source voltage. And this is a 2D problem since it is necessary to solve Laplace equation in 2 dimensions. But luckily, we found a so-called conformal mapping technique, and we were able to obtain these results. So this is finally what was obtained. This part here should not be, this part here is improvable, and currently we are working on that. And it is just a consequence of the fact that we used a really simple, let's say, linear model for the 2D gas depletion with the applied voltage. And the biggest error that we have is actually here in the fringing, since we have really really low values for the capacitance. Now, in order to model output capacitance, additionally, it is necessary to model drain source, since we already have Miller's capacitance. And drain source for the given structure and geometry is actually a fringing capacitance through GAN. And this is on the left-hand side, you can see comparison of the model with the measurements for the output capacitance of this hand. Furthermore, for input capacitance, we needed to model gate source. And gate source is also a fringing capacitance that somehow has, let's say, 2 parts. The first one is directly fringing between these 2 electrodes between gate and source through Algan. And this is quite high. This is actually the highest capacitance that we have in the device. And the second one is related to the configuration of the device itself, which is a so-called multi-finger configuration. which means that we have multiple fingers of drain electrode, multiple fingers of source electrode, and gate electrode. So here you can see this is the also microscope picture from the ESOM, where we were able to identify how these fingers were connected through some source and through some bridges, drain bridges, source bridges, gate bridges. And we were able to obtain additional fringing of almost 100 picofarads just between these areas that connect all the fingers. So with this, we were capable of, let's say, obtaining the full model with full geometry, and also with the analysis that helped us to obtain that physical insight into the emitters capacitance. We obtained this model for the capacitances. And as I said, this is the part that can be improved by modeling of the 2D gas depletion more precisely. And the biggest error is in this fringing part, since the capacitances are really small. So let's summarize what has been done so far. And we can see that fully analytical physical model for drain currents and input, output, and reverse capacitance has been obtained. So this is the first step, and actually this is the main step in a device design optimization for a high-frequency application. Extension of the existing model to a mishamped metal insulator semiconductor structure is in progress. And also some additional things like temperature behavior will be included, and something that is called dynamic resistance or a current collapse phenomena, which is quite important for switching applications, will also be included in the model and taken into account in the optimization process. So thank you for your attention, and if you have any questions.
Thank you very much, Diana, for your really detailed and perfectly timed presentation. So right now we have around 4 minutes for questions and answers. So if there is any question, please. Please,
Yes.
Eric.
So how much is the Fraunhofer Institute, the developer of this semiconductor device, interested in this work? So, I mean, you do this work at this university, I understand. But
Yes.
how much are they interested? Because it's their device, isn't it?
How much are they interested in the work?
Yeah.
Well, we don't have official collaboration with them. We use their devices since our colleague, Marko Tadjer, from this institute in ISAM was collaborating with them. And they already provided devices, and we wanted to model them and test them in our application. And we were able to obtain switching at 20 megahertz in the synchronous buck converter using their transistors. They are co-authors of one paper that we already presented at the conference in US. But maybe in the future we will provide some feedback and maybe obtain some additional information or some additional devices, but we don't have official collaboration with
So
them.
they're not all over you to get, let's say, that modeling.
No, no, they're not.
Purposes, you know?
No, we are not, as I said, we don't have official project with them, so, but we were collaborating.
Any other question?
Okay, what is approximately the power density that you have on the chip? If you know watts per square centimeter, you have idea.
For the Fraunhofer device?
Yeah, yes.
Well, we have, it is rated for 100 volts and for 27 amps.
Something like that, yeah.
Something like that. So size of the chip is, I'm not exactly sure about.
However, but I mean, you have to be very, very careful because actually what you're asking is for the linear application, and this is switching application. So I mean, it's not like that you're going to have maximum current by maximum voltage, because I mean, it would be around 2.7 kilowatts, and it's impossible to dissipate all that energy.
Exactly, yeah. So
What were the specifications of the converter that you developed? It was 20 megahertz?
20 megahertz and
Voltage and power?
average output power of around 15 watts.
But let's say if we made a converter of 20 watts with some 60-70% of efficiency, so if it's how much? Let's say that we had around 10 watts of power loss, it's around 5 watts per device.
And devices more or less?
More or less.
1 square centimeter, I have no idea, it's much smaller.
Well, it has gate width is actually 120 millimeters, and drain length is around 20 microns, and you have 100 fingers, 120 fingers, something like that. So more or less.